This is the second lecture on the series of lectures on supersingular representations of GI to F. So as I said in the first lecture, my idea is to construct supersingular representations of this group where F is a local field and not necessarily QP. So far we have been looking at the representations of GI to QP or SA to QP, SA and QP, GI and QP. But when F is not QP, I mentioned that this this topic is very much in the infancy, and we don't quite understand these representations. So my idea is to give you some construction using some data called diagrams, which also I introduced in the last lecture. So let me quickly recall the notation. So G was GI to F. O was the ring of integers, valuation ring. F has a residue characteristic P. And I had fixed uniformizer. And then inside the K, we have these compact open subgroups I1, 2P Bhavri and K1. And R is inside. Okay, and all the representations are on FP bar vector spaces. So supersingular representations were those representations which do not occur as which do occur as irreducible quotient of compact induction modulo the action of the Hicka operator. So by smooth irreducible admissible representation of G. Then we have seen in yesterday's talk by Shalini that pi occurs as induction from Kz to G of some sigma modulo image of the operator T minus lambda. But I just want to again state the definition of supersingularity. So I say that there is some character. So my definition, so the definition of supersingularity is this. Okay. And what else we want to recall from the last talk? So given any smooth irreducible admissible representation, in the morning talk we saw that we can attach modules over some Hicka algebra. For example, you can look at invariants of pi under pro p Bhavri subgroup. Then this is a module over the pro p Bhavri Hicka algebra, and then one can study this module. And the question is, can you recover the representation pi from this module? So the last theorem which Professor Karol mentioned that this is true when the group is again GA to QP or SA to QP. You can recover the representation from the ECA module. But again, this fails when F is not QP. So in this situation, we consider not just one object, but sort of two objects and a map between them. Okay, so so this kind of object I called as a diagram attached to pi. It's a one diagram attached to pi, and the question was how do you construct representations from such objects. Now this kind of object is no longer a module over some ring, but nevertheless these objects form a abelian category, and you can talk about sub-objects, irreducible objects, and so on. So the I mentioned the one operator or one functor on diagrams which give you again smooth representation of G from such objects. So that was denoted by H0 of a diagram. So something like, so if I apply that H0 to this kind of diagram, then I said that this surjects onto pi, given that it is a non-zero map, which I last time did not mention, but this follows because the map is non-zero, because again one has to go back to the definition of H0, which is, if you recall, it was compact induction of this pi k1 modulo the image of the boundary map. And the boundary map, if you look at the definition again, the image is always supported on two cosets of image is always supported on two vertices. So you can always construct a map, construct an element in the compact induction of this, which is not in the image. Well, so the point is, this is you get a non-zero map, and the question is to study now this object H0 of this kind of diagram, and whether we can construct some irreducible quotients from such a diagram. So this is where I stopped last time, and let me again recall a basic diagram I defined. So let D be a diagram. So recall that this means data from data consisting of a smooth representation of K1, where, okay, so let me again write this K1 was nothing but stabilizer of the G stabilizer of the standard H, which is same as the group generated by Ivavori, and this matrix diagonal 1 comma pi, which you have seen now many times. My notation for this is P, and also so Ki is a stabilizer of sigma I. K1, and K0 is stabilizer of sigma 0, which is the group generated by K and. Okay, so the diagram was data consisting of smooth K1 representation, smooth K0 representation, and a map between them, which is linear for the K1 intersection K0. And we recall that this is a basic diagram. If what were the conditions? So D0 is finite dimensional as a FP bar vector space. The action of K0 on D0 factors through the finite group. And third condition was that the map R is isomorphism on from D1 to I1 invariants of D0. R is an isomorphism. And then I mentioned theorem. That if D is a basic diagram, then there exists a smooth G representation omega such that D sits inside the constant diagram on omega and is same as okay. So maybe some terminology again. So so-called of a representation is by definition is maximal semi-simple sub-representation. It can be zero. And there is a dual, or you can consider maximal semi-simple quotient, and which then we call it as a co-focal. Again, here we recall that we are over XP bar and the group contains pro-P subgroups. So so when you consider smooth representations of compact groups, they need not be semi-simple. That's why we consider these objects, these specific representations, subquotients of a given representation. Co-focal is quotient. Okay, so I want to maybe this theorem might not make much sense right now, but let me give a corollary. First, without saying anything about the proof. So okay, let's see how can one apply this kind of theorem to obtain representations. Okay, so let D be a basic diagram, but now I want it to be irreducible. I will, okay, so after this corollary I am going to give examples of diagrams other than these kind of which already coming from representations, G representations. Then, so D is a basic irreducible diagram. Then this says that H0 of D admits irreducible admissible quotients. Okay, so yeah, so here I will write down. So diagram D is irreducible So D comes with what kind of data? So I have D as D1, D0 and R is irreducible. Yeah, if there is if there is no non-zero, I will describe the irreducibility for basic diagram. So so D is a basic diagram. D is irreducible. There is no non-zero K0 sub-representation of D0. Okay. Since D is a basic diagram, I can identify D1 with I1 invariants of D0 via this isomorphism. Okay. So I can view D1 as a subset of D0. So if there is no K0 sub-representation of D0 such that its I1 invariants are stable under K1 action. You can take, okay, so you can take this as a definition for irreducible basic diagram, or I would have just said that it doesn't have a non-zero sub-diagram, but then if you work it out, you will have this. This is a basic irreducible diagram. Then this G representation has irreducible admissible quotient, and further in bracket with if I put this condition that with dimension of this D1 is strictly greater than 2, as FP bar vector space, if I put this in the bracket, then I will have irreducible admissible supersimilar quotient. So I will also put this here in the bracket. So respectively. Okay, now I will so how this prove, how this corollary follows. So theorem gives me some, there exists the smooth G representation omega such that I have D0 sitting inside omega and as K representations. It's just the embedding of that D inside constant diagram on omega. So I look at, so now on this omega there is a G action. I can consider pi to be a G sub-representation generated by this D0. Okay. So let pi to be this. Okay. And then check, but then this implies that since we look at the maximal semi-simple sub-representation of pi as a k representation. That is the notation for k focal of pi. So pi is a G representation by definition, but I am now considering it as a k representation and looking at the maximal semi-simple sub-representation. So this, what does this equal to? This is equal to, this will sit inside so k d0 and so k omega, which is by theorem again, so k d0. So we have that the k focal of pi is same as the k focal of this d0 of my diagram. Okay, d0 is finite dimensional. So this k focal is finite dimensional, and I am going to prove one theorem which will imply that if right now I have just mentioned it as a black box. So it theorem says that if the k focal of smooth G representation is finite dimensional, then the representation is admissible. So this tells me that pi is admissible. So recall that pi is admissible, meaning given any compact open subgroup, the invariant vectors under that compact open subgroups form a finite dimensional vector space. Okay. So this is just a black box. I will prove this once I talk about injective envelopes. Using that, I will show that a smooth G representation over FP bar vector space is admissible if and only if its k focal is finite dimensional. Okay, and I want to show that it is reducible, and further if we have this condition that it is super singular. So again this is, okay, so irreducibility. What I want to show is that if I take some non-zero sub-representation pi prime, then it is equal to pi. Okay, so let pi prime be a non-zero G sub-representation, and then we can construct the diagram which is a proper sub-diagram of a given diagram as follows. So you just intersect pi prime with d0. Yeah, this is same as pi prime I1 invariance intersected with d1. You can use this definition, for example. So I will contract the irreducibility of diagram. So I claim that pi prime intersection d0 is a non-zero k0 sub-representation whose I1 invariants are stable under k1 action. So the I1 invariants, why they are stable under k1 action? Because d1 is stable under k1 action by the definition of a diagram. Pi prime I1 is stable under k1 action because pi prime is a G representation and k1 normalizes I1. So the intersection is stable under k1 action. You have to check that this is equality. So that means I find some k0 sub-representation of d0 whose I1 invariants are stable under k1 action. Which contradicts that, or not contradicts. I will show that pi prime is equal to pi. So then this implies that if I consider pi prime intersection d0, I1 invariants inside pi prime intersection d0, right? Oh, sorry. to d0, which implies d0 is inside pi prime. But by definition, pi is generated by d0, which implies pi is equal to pi prime. So this is standard kind of technique in these arguments. You might have also seen this yesterday in her talk, that something is generated by weight, and suppose any sub-representation also contains that weight, then it has to be irreducible. So this is kind of argument here. And super singularity, so here we use the classification of Bartholdi. So note that by definition, again, the way pi is defined, the I1 invariance has dimension greater than or equal to the dimension of this d1 of the diagram, and which is greater than 2. Now we know that from Bartholdi that super singularity is same as that. So this is if and only if pi is not a subquotient of a principal series. And any subquotient of a principal series, its I1 invariants have dimension less than or equal to 2. So this okay. So some of this. So maybe I will also write down. Not a subquotient. So and okay, so such subquotients have I1 invariant space of dimension less than or equal to 2. So if it is a irreducible principal series, then its I1 invariant space is equal to 2. If it, otherwise it has trivial character. When it is not a irreducible principal series, it contains a character and a twist of Steinberg, both of which have I1 invariant space of dimension 1. And Bartholdi says that super singular is same as it is not a subquotient of principal series. Okay, so this
so here pi prime intersection d naught can be 0, but it's not because they intersect in the circle, is it?
Yeah, you are right.
Okay,
and pi prime intersection d0 can be 0. Yes, you are right. Pi prime.
But they intersect in the circle.
Non-trivially with the circle of pi, because it's a sub-representation, non-zero. It has some weight common with pi, and circle of k pi is circle of k. So, there are, maybe I didn't say all the details here.
And how is it a quotient of H naught d? How is pi a
quotient of?
We want to say pi is the irreducible admissible supersingular quotient over here, right?
So why this is a quotient, you mean? The way I have defined why it's a quotient of H0D?
Yeah.
So this will again follow because just the diagram. So D will be sitting inside, if you take this definition, it will be sitting inside constant diagram on pi, right? Because pi contains, you take a constant diagram of pi, okay, and then you get a quotient of H0D2. Yeah. So I define pi to be this representation. Then check that the diagram, this diagram that we start with is sitting inside this diagram, constant diagram of pi. that clear? No? Which part is?
The diagram just means I1
Mhm.
What is this diagram?
So this diagram is nothing but pi to pi and the map is identity. This diagram is D1, D0, map is R, and this thing is a sub diagram of this. And
So what?
then you take the question was why this pi, the way this is defined, it occurs as a quotient of H0D, because in the corollary I am saying it admits irreducibility.
So finish the proof.
Okay.
What did you say? So why is
Then you have a non-zero map from H0D to pi.
what is that map made by the
Huh? This map.
previous map?
It's an implication sign.
This is
But that's an implies. I can't like you have to press the jump harder where it's not to be equals. Okay, that's implies.
yes. This implies there is a surjection onto pi.
Pi is x0 of identity.
Yeah.
X0 of
That.
is pi
Oh.
is x0 of the function.
Okay. Right.
Why is it surgery?
Okay. So non-zero is non-zero. I said that image of the boundary map is always supporting at least two vertices. That one. So it is, then that gives you that it is a non-zero map, and we have showed that it's a map of G representation that follows again from the constructions, yes. And pi is irreducible is this argument, so it has to be satisfied.
The irreducibility is very complicated. Why is it so complicated?
It is two line only.
Why is it it's very formal and I can just take something in the say something in the circular pipeline is not something like
Yeah, so circle of pi prime is non-zero. That implies this representation is non-zero.
yes.
And I gave a definition of irreducible diagram here. Yeah, I mean, if one, I don't. This is the only way, I suppose.
Sure, it's correct. It's just that
Huh?
so you rephrase the definition of irreducibility in some more complicated way, and then you're using that. Yeah, but anyway, okay, it takes some time to.
Yeah, I said that you have to figure that out. That sub-object means yesterday, the day before yesterday, I said what a sub-diagram means. You have arrows, right, which makes the diagram commute. And here, for a basic diagram, we have a one more condition that D1 is isomorphic to I1 invariants of D0. Using that, one can check that this is equivalent to saying that D0 is irreducible. Okay. Okay, so this is all about general theory I wanted to talk about. Now we can, so now what is our next goal? Is to construct basic irreducible diagrams. Okay, and once you have a basic irreducible diagram, you have a you know that the irreducible admissible super singular representation exists from this corollary. And so for that I recall some representation theory of finite groups. So you are already now familiar with FP bar representation of GL to FP. Now we need so this theory generalizes to GL to FQ similar way. So let me recall some facts. So this is J to FQ, and every time we are over FQ bar. Okay, so I will just mention things that I require. So how do so what are the weights in this situation? So for J to FP, you know that every weight looks like was described by two integers, A and B, in some range. The same thing is true here. So let me write it down. My notation is a bit different. So the irreducibles here look like I will write it as sigma r bar m. So where r bar is now f tuple of integers r0, r1 up to r f minus 1. And what is this representation? Sigma r bar m. It is nothing but symmetric power r1 r0 f bar square tensor f bar square dot up to rf minus 1 f bar square. Except that you have additional action of the Frobenius here. So let me these are not exactly symmetric power representation, but together with some composition with the Frobenius map. So for that I am writing it as this. So f minus 1. So where so the underlying space of sim R J F bar square is the space of homogeneous polynomials of degree homogeneous polynomials in two variables of degree Rj. And how does the Gi to FQ matrix acts on it? So if ABCD is in Gi to FQ, it acts on X by first you apply the Frobenius map to the entries. That means taking the p first you take p power jth power of the entries. So this will be a power p power j x plus c power p power j y, and on y it acts by x.
You want the variables to be x, j, y, j?
Huh?
You want the variables to be x, j, y, j or just x, y? Variables first.
Oh yeah, okay. Okay, maybe we can be more precise. Okay, so here it will be. And sorry, so this was just the R tuple, and then one has the determinant of a matrix to the power n. Now so these entries Rj's vary between again 0 to p minus 1, and m vary between 0 to strictly less than. Now it will be q minus 1. Okay, so this is how given irreducible representation, any irreducible representation of J to FQ over FQ bar looks like. And sometimes I will also just write such a representation by just these two R bar and M instead of, and forget sigma. So maybe when Q is equal to P, I only have sigma r0 comma m, and this was the same weight as r0 plus f r0 plus m comma m. Okay. So again some notation I want to fix now. So inside GL2FQ we have upper triangular matrices. I will denote them by BFQ, and inside here upper triangular unipotent matrices UFQ. And similar to GI2FP situation, if you take a weight and look at the U fixed vector, it is again one dimensional. So sigma r bar m UFQ is one dimensional. So it is a character of BFQ modulo UFQ. Again, similarly, this normalizes upper triangular unipotent. Upper is one dimensional, and hence a character of which is isomorphic to the finite torus FQ star FQ cross FQ cross. So any character here is going to look like FP bar valued character is going to look like product of two characters, and you know here how characters look like. So maybe whatever given by this diagonal AD sending to A power R plus M. So okay, let me maybe make some comments. So A power R comes by the fact that the U invariant space is again given by the polynomial x0 tensor x1 tensor x2 up to xf minus 1 whole x0 power r0 tensor x1 power r1 up to xf minus 1 power rf minus 1, that kind of monomial in now f minus 1 variables. So that gives you this a power r. I did not say what is r. So given such a tuple, we just take r to be rj pj p power j from 0 to f minus 1. And then we also have determinant that will be ad power m. So this is nothing but a r plus m d power m. Okay. I will denote. So again, this character we denote by chi r bar comma n. So given a character on the U invariants of a weight, I have a character, or given actually any character of a torus, I can conjugate it by this S, which was denoted by W in the previous talks, nothing but it's the non-trivial element in the while group. So this is the conjugate of, sorry, this is 1 minus 1. Conjugate of by base, meaning you take you evaluate this on something in B by taking chi r bar m of S B S equals sorry, something in the torus. How do I okay, I will put it down. So basically, what does this conjugation by this element do? It basically switches these two entries, A to D and D to A. So the character will become D power M and this determinant will remain the same. So you can check that this is nothing but chi of now P minus 1 minus R bar comma R plus M. Okay. And then we have this one is the characters of what is this? Yeah, so this is basically P minus 1 minus R0 comma P minus 1 minus R1 dot dot P minus 1 minus R minus 1. This is this. The first entry. I am denoting is that okay? Okay. So let us I forgot this finite torus T FQ is quotient. So characters of TFQ such that characters chi of TFQ such that chi is not equal to chi s. So it may happen that so when let me first finish this. So it may happen that you get the same character by conjugation by S. So the characters for which it is not equal to its conjugate, they are in basically you can one-to-one correspondence with weights of GI2 FQ, excluding which kind of weights we don't want. So except this kind of 0 bar comma m and p minus 1 comma m. Okay. So I don't want to do this because these are very easy kind of checks and I'm just stating some easy verifiable things here. Just to introduce some notation here. Yeah. R. Where? Here. So that R is this R tuple. Yes, this R is this R. So when R is without any underline, it is this. So the notation I want to introduce here is that so given such a weight which is not coming from, so how many weights are here? We are fixing the first entry, first tuple, F tuple in both, and M can vary over Q minus 1 elements, Q minus 1 integers. So there are 2 Q minus 1 weights here, and we are excluding those 2 Q minus 1. And you can check that total number of weights is 2 square minus Q. And we are excluding 2 Q minus 1. And characters, you know that they are in, they will be, the number of characters will be the size of this group, which is Q minus 1 square. And you can just check that this should be equal to Q minus 1 square. q minus 1's and minus total number of characters are q minus 1 square, and we are excluding those whose conjugate is the same, so those will be um, uh, okay, I just wanted to say that, okay, please. So that so given a such a character, I get some weight here. The map here in the other direction is nothing but you take a weight sigma, and it is mapping to u invariants of sigma. Okay. So the corresponding weight to a character I will so sigma will go to chi, and let me just write sigma s will go to chi s. So this sigma s is well defined if chi belongs to this. Okay. So there are some facts I want to mention about. So let's look at now principal series of GL to FQ. Principal series of GI to FQ. So this is induction of some character from PFQ to GI to FQ. Yeah, this is the U invariants of sigma. Yes.
It's not possible to read either of those sigma. Sigma subsubgroup. What is that subsubgroup?
Where here? Or here?
Neither of those. The middle.
Middle?
Oh,
Yeah,
that's
so
not, that's not sub something. That's only induction.
no, it's not. Okay, so I am fixing some notation here. So suppose a character chi here corresponds to some sigma, then chi s will correspond to some unique weight, and I am denoting that weight by sigma upper s. That was the notation. It is not conjugate of. No, it is. So, okay, again, this notation is misleading, but usually sometimes they denote by square bracket s, but I don't want. Okay.
Then 3 minus 1.
Why is it?
It's written on the board. 3 minus 1 or bar, comma, or percent. That's it. And there, it's on the top.
No, her question was whether sigma upper s is a conjugate of sigma by s. Does that even make sense?
It makes sense. It's a sigma s is defined as the top of the board.
Yeah.
No, not the by second line.
Yeah. Yeah. So, if sigma is of the form sigma r underline n, then sigma s will be, it will be this. But r plus n, yeah. Yeah, sorry, it does make sense. Yeah, it is not the conjugate of sigma by s. but you can of course take a conjugate of sigma by S also. Yeah, you will get so you can ABCD will become something like principal series. So it's the induction of a character from Borel FQ to GA to FQ. Note that this has what is the dimension? The index of VFQ inside GA to FQ. The index is Q plus 1 as dimension Q plus 1 as and the dimension of a maximum, the largest dimension of a weight you can compute from here. Each symmetric power representation has dimension Rj plus 1. Rj vary from 0 to p minus 1, so it can be at most p. There are f many, the tensor properties of f many vector spaces, so it will be p power f. P power f is q. So principal series is never irreducible in mod p setting, and hence is not irreducible. So this is something very this kind of phenomenon you can see only over FP bar. Maybe okay. So I have mentioned here that for Q equal to P, I will write down how this principal series looks like. So one has this short exact sequence, so 0 sigma b minus 1 minus r0 comma n. To induction of chi r0 comma n p fp g to sigma r0 n 0. One has a short exact sequence. So the principal series has these two Jordan-Holder factors or irreducible subquotients given by these weights when you are reducing from a character of this form. And this short exact sequence splits if and only if, in general it doesn't split. Yeah, if and only if again when we are in this situation that so when R0 is either 0 or p minus 1. Actually, this theorem, the splitting is even true for when f is q is not equal to p, but in general, so when q is not equal to p, and if you are inducing a character coming from these weight, it again has only two weights as Jordan-Holder factors. But in general, when it is non-split extension, or it is not true that it only has two Jordan-Holder factors. So in general, let me. It is same, right? When p equal to q. principal series has 2 power f Jordan order factors. Okay, these are all is multiplicity free. And you can check that the focal and co-focal so the principal series of induction of chi R M so by Frobenius okay I will maybe leave it to you to see that you can use Frobenius reciprocity plus some work it's in today's exercise that the focal of principal series here is the weight sigma r n s and the co-focal of principal series is sigma r. So I couldn't hear you. For which, yes, otherwise it, in general, maybe I should have it. Okay, let me see that. Chi R bar M. Oh, sorry. In general, when. No, it is on when chi is equal to chi s. I mentioned it here. It's only these two weights appear in the Jordan factors of principal series for any q.
No, not multiplicity. But the number of Jordan factors.
Number of Jordan factors is 2 when chi is equal to chi s, and it is it is also direct sum of those two factors.
Q.
Yeah, even for q. But the multiplicity freeness is true. In that situation also these two weights are different. Dimensions can the one weight is one dimensional, the other is q. So it q plus 1 is. Okay. Yeah. So okay. Why I was giving some facts about representation theory, because recall that we were considering basic diagrams, and in the basic diagrams the D0 object, the action factors through GL to FQ. So if we want to construct a basic diagram, we as well look at the GL to FQ representations and then inflate the action to that K0. Okay. So now I will give some examples of basic irreducible diagrams. Okay, so let D1 D0 D be a basic diagram. First, so basic diagram means that so we have K1 action on D0 in I1 invariants of D0. Okay. By definition, basic diagram, this R is isomorphism of D1 onto I1 invariance of D0. So we have a K1 action on this space, but what is K1? It is generated by Ivahori times Ivahori and that anti-diagonal 1 comma P pi matrix. Okay. So this space is already stable under I action. I just want to put the action of T. We will recall that T was 1 pi. Okay, and we also know that T square is nothing but diagonal pi, and we know that diagonal pi acts trivially on D0. Again, it is included in the definition of the basic. So what do we want? To give an action of this matrix on this space, I want order to bijective linear map. Okay, is that clear? So this is my D1. I am identifying D1 with I1 invariance of D0 via this isomorphism. Okay, R. Yeah, and I will say again and again. Okay, so to give a T action on this thing, I want to give a order to the bijective linear map on this space. But not just that, it also should. Since T also normalizes I1, it should also the action should be compatible with the characters which are appearing in this T1. So let's say, so for V in chi, which occurs as a character in D1, so maybe I'm going too fast or I don't know. So D1 is a representation of which group here? In the definition of a diagram, D1 is a representation of K1, which is a group generated by I comma T. So here we are taking I1 invariants. So D1 K1 action will factor through I mod I1. Okay, but I mod I1 is what? I mod I1, you can check that this is same as BFQ modulo UFQ, which is the finite torus. So these are the as I representation. D1 is a direct sum of characters of this form. Okay, right. And so for V in chi. Let me so I want to define what this TV. So TV should also be inside D1. So TV will also be some character of I. So let's first find out which character it is. Okay. So I of TV, where I is in I, is same as T inverse I. V. We know that T normalizes I. So this is same as T of chi I. So this chi as this is chi is I mod I character inside D. V, which is same as this. Sorry, here the T inverse IT. If you do this conjugate any element in I, Ivahori by this element, the action of character is same as chi S on that I. Everything is factoring through finite group here. You can check, huh? Yeah, so I was saying that D1 is a I mod I1 representation, right? So why? So I am taking some character in the. So I mod I1 is what? This is a torus, and also the order is co-prime to P. So it will decompose as a direct sum of some characters of a torus. So I am taking some character chi in this T1. Okay. Okay. So we have this thing. So this is that chi is id. So if I take a vector in some character chi, the t action should take that vector to chi s character of I. I want to define a t action on d1, but this is a necessary condition we are getting from just this the observation that t normalizes I, and the action is the same as the conjugate by s on the finite group character. And okay, so what I have written. So if so, the action of t, if exists on action of t on d1, maybe if exists, should define a linear bijective map on the chi isotopy component from chi isotopy component of d1 to chi s isotopy component of d1. So it's a bijective linear map.
So why should the conjugation by T be conjugation by S? Sorry.
Oh, you can check it this. Okay, I don't want to check it. You can check that conjugation by T. When factored through finite group, it will be the same as a conjugation by S. Where this is. So what are these V chi and V chi S? These are chi isotopy component. Okay, maybe people are not familiar probably with this word, but I will just write as this chi isotopy component means you are taking all the chi's together which are in D1. So that is the chi isotopy component. And then similarly V chi, this is that. Okay, so and this is the only compatibility we have to check, because to give a K1 action we only need to give a T action and whether it is compatible with I action which is already on D1 or not, we have to check. And the only compatibility is this one, that one should have one should have number of chi's in D1 should be equal to number of chi's in D1. This is what this explanation gives. So let me write this. Yeah.
Not a formal notation and no example.
Yeah, but yeah. Right. So to give an action of T, maybe a compatible on this D1, what do we want? A necessary and sufficient thing. It is necessary and sufficient that is the chi of multiplicity of chi, some character chi in D1 is same as the multiplicity of chi is in D1. So this is what I was trying to explain there. Now let's look at examples. Let's try to construct examples. that example. So what I can do, I will just take D0. So D0, we call that it's a finite dimensional GA to FQ representation, and I want to find out such representations such that on U invariants, when I look at the characters, the multiplicity of any character should be same as the multiplicity of its conjugate. That's the only requirement I want. So I can just take D0 to be weight sigma, some GA to FQ weight, direct some sigma S. Okay. Yeah, and then so then we know that D1 is, and I define D1 to be the U invariants, U F Q invariants of D0. That will, they will look like chi direct some chi S. So again here this, if you recall that the definition of sigma S was this was well defined when chi is not equal to chi S. Okay. So let me have that assumption here, and okay. So so this is the so this is a D0. I get a GA to FQ representation, sum of two weights. I get some B representation, which is sum of two characters of B mod U, and I want to now define a T action. I can take so let me write this as a sum of two vector spaces. Choose some basis E chi of chi, and E chi S. I will so define the action of T on D1. You can just take I mean, by taking E chi to some non-zero multiple of E chi S. It's lambda. So there are, so this defines a basic diagram. It is also irreducible, and all these things I won't be checking. But one important point I want to here mention that, see, this gives you a diagram which depend on this scalar a priori, but all these are isomorphic. All these diagrams are isomorphic. I want, so the point here is that you can always choose, so what is an isomorphism of a diagram? It's an isomorphism of, so D0 to D0, if it is an isomorphism, so I have D which is D0, D1 to D0, and the same diagram again, D1 to D0. So I say that I have isomorphism from D to D. If I have isomorphism on here, which is isomorphism on D1. Okay, so this is the definition. So if I why all these diagrams are isomorphic? Because what are the maps from D0 to D0? This is the sum of two irreducible representations. So all the maps from D0 to D0 are given by some two scalars, and you can always choose those scalars such that maybe by taking inverse of one and multiplying it with the other, you get lambda. So there is some check to be done here. So you can always find an isomorphism between two diagrams corresponding to different lambdas here. But now the second example is important. Again, a similar kind of situation, but now the diagrams will be non-isomorphic, and we will have as many diagrams as the cardinality of FP bar star. So what is the second example here? So the second example is the principal series for GL to FP. So if you, I mentioned it as a fact that principal series of GL to FP. So okay, so here Q is equal to P, and D0 is induction B F Q to GL to, so FP of chi. And I want this to be non-split, so I take chi not equal to chi s. So again, this is, so now this is a non-split extension between two weights, and those weights look like sigma and sigma s, look like they are actually sigma and sigma s if U invariance of sigma is this character chi. So again, in this case D1 is same, D1 will be D0 U, FP invariance is again chi plus chi s. But now D0 is different. So here if I define the same, so okay, since D1 has equal number of chi and chi s, I can again define the T action as before. Okay, so here I have FP bar, I direct sum, same as before, and define T action same as before, but now these diagrams, this will give rise to different diagrams as you vary lambda, and so define the action of T as before. Action of T as before. In the exercise, you will show that even though this principal series is not irreducible, the only endomorphisms are still just the scalars. Okay, and using that fact, one can check that you cannot find the isomorphism if your lambda is different from lambda 1, lambda 2 are different. Define the action of T as before. Gives rise to non-isomorphic, again irreducible basic diagrams. Basic diagrams corresponding to each. And in the last 2-3 minutes, I want to just say a few words. What about the now corresponding G representation? What we can say about the representations of GL12 coming from these diagrams? So for this is again theorem by Broy, that for F equal to QP, H0D with in example 2 gives all ramified principal series representations of GI2QP. With trivial action of P is equal to P, so diagonal P, and
Gives here means that all these are quotients of H0D.
no,
It's homomorphic.
it is H0D itself is a ramified irreducible principal series, and ramified meaning it has a so it is a tably ramified, so it has K1 fixed vector. So in the mod P setting, it's either unramified or tably ramified. There is no this this gives you a representation which has fixed vector under K1, the first principal component. Sorry? Yeah, not unramified. So it unramified we have seen in this talk. Yeah, so, it means it has a fixed vector under K, but these don't have fixed vector. Okay, and one last remark. So H0D with D in example 1 gives all again irreducible, admissible, supersingular. Okay, these adjectives are also here, irreducible and they are admissible. Irreducible, admissible, supersingular representation of GI2P. With trivial action of again P. So you can you can observe that if I fix the action of my P, there are only finite since there are only finitely many such pairs of weights, right? There are only finitely many basic reducible diagrams I can construct as in example 1. So there are only finitely many irreducible, admissible, supersingular representation of GI2QP with fixed action of with fixed central character. So I just wanted to mention, and okay, and in the right, and in the maybe I don't have time today, but so I just want to maybe say that we can generalize this situation which is observed in 2 for higher Q to obtain families of supersingular, irreducible, admissible representations. You may wonder why I am saying supersingular, because in this situation the example 2 gives rise to principal series representation, but this is a very specific to GI2QP. Okay, so let me see what I wanted to say. Okay, generalize in the sense that we don't take the principal series when Q is not equal to P, but some D0 which looks like which more or less doesn't look like principal series, but it looks like sum of extensions, again non-speed extensions. But yeah, I mean, I will maybe explain this next time. So yeah, one can generalize this kind of situation to Q which is not P, not with the principal situation, and then one can use the corollary I mentioned in the beginning to get many families of irreducible supersingular admissible representation. That would also explain the fact I mentioned in the beginning of my first lecture that this compact induction modulo, the image of T, does not have finite length when Q is bigger than P. But that will, I will do this in the next lecture. Okay. Question.
So do you get the super singulars also for the trivial application because chi is not equal to chi s, right? In the example 1.
In example 1,
Yeah, but yet you claim you're still getting all irreducible supersingulars.
yeah. So in my talk, I sort of defined this notation sigma s when chi is not equal to chi s, but you can also have a trivial trivial representation here and the corresponding all p minus 1 and d2.
Okay.
That will also give you super singular.
Lambda will depend on T or lambda is fixed?
So lambda does not depend on t. Yeah.
Depends on T, right?
Yeah, it will depend. Change the calculate side to side. You have to multiply by appropriate fraction.
Sorry, say it again.
Maybe you have to multiply by appropriate fraction because torus he acts on e chi by one character and it acts by another character on chi.
T should be just a linear map from this vector space to this vector space. So it has to be some multiplication by scalar. It doesn't depend on what chi and chi is.
No, on T also it's present.
Yeah, it does not.
For every T, that lambda is constant.
Yeah. Oh, okay. No, this lambda is constant.
It will
T
depend.
T is just one element. I don't. T is this interval of 1 pi.
Oh, okay. Sorry. I thought T is in torus. Okay.
Oh no. Okay. T is not in torus.
For future funding, one should say that you're looking at the dynamics of T, right? It's a dynamical system.
Mhm.
You might get some grants in the future by using such words.
Okay.
Seriously. No, I was saying that in number theory you have discrete mathematical analysis and now there's also some dynamical system, right?
Yeah, there is some combinatorics. There is a lot of combinatorics involved here.
Dynamics of the T operator. It's moving things around.
Yeah, but
Right.
that is also.
This action of